This is a Singer FM10C frequency generator. These were made sometime back in the early 70s, I believe. And I have two of these. This is a donor unit that I'm going to try to get working here. This is basically a heterodyne frequency generator, and it'll generate from 50 kilohertz to 512 megahertz. And it has 8 decade controls, you can see here, that you dial in your frequency. And there's also a variable one on the end here. And this isn't like your modern phase lock loop synthesizers. The way this works is they take a 10 megahertz time base, and by frequency multiplication and division and a lot of filtering, they generate your output signal, which comes out on this connector here. The output is adjustable, comes out of the RF output here. You need to add a 40 dB attenuator for the control to be accurate here. It is adjustable from 0.1 microvolts, from 0.05 microvolts to 5 microvolts, or minus 90 dBm to minus 130 dBm. And that's on the output connector here. You can also connect an input signal at this connector here, as long as you don't exceed a half a volt. And the sensitivity of measurement is controlled by this control. There's a high and a normal position, and then there's a variable here. You can vary the level here. This is the RFM1 module. This is generates the CW signal that's used in the unit. In the center is the FIM-3 module, and this is a frequency error meter which can measure error from on 3 different ranges: 1.5 kilohertz, 5 kilohertz, and 15 kilohertz. Directly on the meter here. It's got a light here that says beat, that when the frequency that the generator is set to and the input signal coming in, as they approach the same frequency, this light will start blinking until at 0 beat. It either stays on or off, and that means the two signals are in phase at the same frequency. You can't hear frequencies as you 0 beat a signal. You can only hear down to maybe, I don't know, 40, 30 cycles or whatever. By watching the light here, you can set it right down to 0. And then on the right hand side here, this is the ODM1 module. This is for FM, and you can measure deviation directly on the screen here. You can see the numbers here, and there's different ranges here from 1.5, 5, and 15 kilohertz. The unit also generates audio that can be used to frequency modulate a carrier to apply to a signal to a radio receiver. So basically this is set up for FM radios only. You can get modules for AM that plug in here. There's different modules available. I don't have any other modules. These are nice units. The other one I have on my other bench on the other side is working, and like I say, this was going to be a donor for that one if it had problems with it, but I'd like to get this one working. I know that some of these switches are intermittent, so I'm going to address that. And also this deviation monitor is not working properly, so I'm going to have to work on that too. So stand by and we'll look on the insides here and see what we find. I thought I'd give the old Clegg signal generator an exercise today. So I'm running that into the input of the service monitor. As you can see, I've got the Clegg set at 2 megahertz, and the singer set at 2 megahertz. And you can see we're not quite on frequency. I'll adjust the, as I bring the Clegg on frequency, you can see the meter, the frequency air meter change. Kind of hard to adjust. I think what I'll do, I'll put the 100 hertz on variable and use the variable out. Yeah, it's still drifting. This hasn't been on a long time. Here you can see as I vary the variable 0 to 100 hertz, I can slowly vary the, and you can see the frequency air meter changing. This is on 1.5 kilohertz air. So there's about 300 cycles. Let me go the other way. .300 in the other direction. When we get to 0 beat, you'll see the light here blink. That's pretty close. But you can see it's starting to drift as the beat note changes frequency. The ODM1 unit is not working right. This module has a problem with it. I have a feeling the drifting is probably from the Clegg drifting. The Singer has a better time base in it. That's been on for about 10 minutes, so should be fairly stable. The Clegg is set at 20 megahertz and the Singer is set at 20 megahertz. And you can hear, and as you watch the frequency air meter, as I tune through 0 beat here, pretty touchy. Yeah, there we're close. Yeah, but it's still drifting. This one is going to drift for a while. This has been a little mechanical modulation here. With the new synthesized generators, it's hard to get used to these old ones. I still like to mess around with these, even though it's brings back memories of the old days. Amplifiers that oscillate and oscillators that won't. Well, as much as I like my old Clegg, I don't have time to wait for this thing to drift up and down. I just turned on this old HP 8656B. I just turned it on about a minute ago, and already it's within, let's zero the thing here. Already it's within 100 cycles of 0 beat. So yeah, these are nice old units, but just don't have the patience, I guess. So the HP is set on 20 megahertz, and watch what happens if I take the 100 hertz and I went 100 hertz high, and it's pretty close. think what I'll do, put it on variable. And as this shows here, a little over 100 hertz using the variable. The way this works is each of these decades up to the 100 kilohertz have a position that shows V. And if you put it on V, that basically overrides the decades to the right of it and allows you to use this variable here. So this is basically varying 100 up to 100 kilohertz. See if I can find the... Yeah, it'd be kind of tough here. Here you can hear it. Yeah, it's a little too touchy. So let's go down to the 1 kilohertz on V for variable, and I can use a little easier to adjust it to 0 beat now. On the level, you need to have it in the operator range. If you get too hot a signal, the overload light will come on. Too low a signal, and these lights will be out. So once you're in the operation, once the operator light's on, you know you've got a good signal here. Got to find out what's wrong with this unit. The ODM1. This one's got a problem somewhere on the scope here. You can also measure off-air signals using a lip antenna in this case. I am listening to a local FM station, 88.7 megahertz. I have the decades set up on that frequency. You have a speaker here and a volume control. You can listen to it. Like I say, this scope is not working right. This isn't accurate. You can see the operate lights on. Here's the frequency error meter. You zero it with this knob, and then you can measure 15, 5, or 1.5 deviation. When they stop talking, this is a FM broadcast station, so when they're not talking, this should go to 0. Even on the 1.5 deviation range, this should go to 0 between speaking. And there you can see when he stopped talking, the error meter went to 0. Assuming that this radio station is on frequency, which I do. So it's convenient that you can actually measure deviation of an off-air signal once you get the deviation monitor working, that is. Luckily I have a manual for this unit, which is quite extensive. As you can see, it's got all the schematics for all the modules. It's got board layouts and everything like that. You really need to have a service manual. You're working on one of these. Here's a block diagram of the unit. Starting on the left here, you've got your time base, which can be internal or external. There's a switch here. And power supply. I won't go into this. This is pretty complicated. The manual explains all these circuits, but basically what they do, each of these decades, they take the master oscillator here and they divide it and multiply it, and then it goes through a series of mixers and filters, and by setting in your dials here, you end up with an output on this side that goes into the modules, which are shown here. RF module and the modulation module and the frequency error module here. So all the generation's basically done by multiplying, dividing, and filtering a 10 megahertz reference. And like I say, you can connect this to an external source like a rubidium standard or a GPS standard for a more accurate results there. As you can see, there's a lot of mechanical contacts in these switches that are over 50 years old, so this thing's going to need a little TLC if I'm going to get it working properly. Uh-oh, I just broke through the warranty sticker. I bet they won't honor the warranty now. After 50 some years, I guess I don't have to worry about that. These boards are not in sockets, but fortunately they're easily removable. They slide out and you get access actually to both sides of the board here, and then they just slide in. I guess that was a good idea because sometimes the edge connectors can present a problem. These things are really well constructed. Kind of reminds me of the Cushmans, but I guess it's from that era. Are these gold-plated contacts? Yeah, they might be. Here's a view of the bottom of the board. My other unit has the high stability time base. This one doesn't. This has the 1 part and 10 to the 6th. The high stability option is accurate to 1 part 10 to the 7th. Looks like this is the power supply section here. I can test the voltages. Here's a board. I gotta find out what these boards are. I'll look in the manual. Here's a couple 7490s decade counters. Not sure what they're for. Very clean unit though. It's nice looking. I bet a lot of these caps here may have high ESR. I'll check all them in the power supply. Some of them will probably need changing. One thing I noticed, it's kind of nice. Back in here, I have access to the back of those Amphenol connectors on the plugins. So I may not have to come up with some kind of an extender mechanism. So I'll be able to take some. It's kind of tight, but I should be able to get a probe in there. I checked all the electrolytic capacitors here, and they're all within spec, although this one with a red X was right at the mark. I may replace that one. But these old capacitors still are testing good. I wish I had $1 for every good capacitor that's thrown out or replaced. Just because they're old doesn't necessarily mean they're bad. Really need to check them. And the ripple's alright. Checking on the scope here, I'm measuring the plus 9 volts. The ripple is supposed to be less than 2.7 millivolts, and it's a little bit less than that, but pretty close to it. So power supply is looking good. This is the regulator board here, and these leads, the large leads here that are coming, the yellow and red, they run up to the 2N3055s up here on the external transistors for the regulator, the pass transistors. Here's a view of the power supply. You can see those two big blue caps, 1500 at 25. They go through the 2N3055, and then the terminal board where I was measuring the ripple is this 4-terminal block here that has the 9 volts DC outputs on it. Nuts. I dropped a little teeny washer and it went somewhere in the carpeting. Well, don't worry, I'll find it next time I vacuum. All the switches have been cleaned. I've verified the power supply is good. Visual inspection went okay. This ODM1 unit is still not working correctly. This should be a straight line. The vertical's working, horizontal's working. The focus is doing something, but there's some type of a problem here. I've had this counter since 1978, and it's never failed me, and it's actually calibrated to this GPS discipline oscillator here. So let's see, I think I'm going to, now let's see, let's try this. 462 61116. 1 1 1 6. Yeah, it's pretty close. It's about 150 cycles off. And I know that this oscillator time base has not been adjusted for who knows when. So I think I'll do that. I'll connect the output. There's an output on the back you can connect and run an input. Or I can measure in the back of the unit, measure the output frequency. I can actually, what I think I'll do, I'll use the scope, put the GPS oscillator on channel 1 and the output of this time base on 2, and then I can adjust it so they're in phase. That's probably the best way to do it. So I'm trying to see the next step. I think I'm going to pull this module out here, the ODM1, and see if I can figure out what's wrong with that. I've substituted another ODM1 module from my other working FM10C. It's got the little hood on it. Ooh, it's got a little dust on it too. Don't tell Patty. Anyway, got an HT here, an HTX202. And I'll transmit here. 145, 255. And looking at the unit here, test 1, 2, test 1, 2, 3. Hello, hello, test. Now that's what we want to see. And you can see the frequency error is showing about 200 cycles high frequency error, which, let's see, 145. And like I said, I haven't adjusted the oscillator in this unit yet. Hello, 1, 2, 3. So anyway, we're going to have to work on the ODM1 unit. It came out of this unit and try to find out what's wrong with it. Anyway, for now I think we're going to close this one down before it gets too long. Anyway, these are nice units. If you see one at a Hamfest, pick one up. Might need a little work, but they're pretty nice units. Easy to use and quick. Thanks for watching. Bye for now.